logical order because of how we smush all the terms together. So remember I said, memorize these in pairs. Okay, so this is based on energy. How do they get their energy? How do they get their, what's their electron source? And what's their carbon source? Because then when you smush all these together and make these various terms, that's how they always name them. You know, so photo, litho, auto, it's by energy, electron and carbon. It's how you traditionally smush all these terms together. So I thought that would be maybe a little bit more logical to order them in this regard. Okay. So that's the only thing I changed. All right. Let me pull up. And I will post this, of course, when we're finished with it. But based on your feedback, I wanted to kind of get into kind of picking apart the different topics and trying to clarify what level of detail is needed. So when we looked at glycolysis, we broke it down into 3 stages. Many of you said you're pretty comfortable with glycolysis because you've either had biochem or are currently in it. But really, again, it's not memorizing step by step by step by step in detail. It is, okay, we know there's 3 stages. So basically, I'll be asking about those 3 stages and if you look at each stage, what is going on. So I forgot to pull up the actual thing. Let me bring that in. And I'm going to do this. Let's see. All right. Okay. So here is glycolysis. So stage 1 is the tan section. So what is going on in stage 1 of importance to the microbe? Pardon me?
Adding phosphate.
Yes, you got it. So adding phosphate, and the flip way to say that is using ATP, right? So it's priming the pump. The microbe has to add phosphates to to glucose. Unless I say otherwise, let's assume it's glucose coming in, okay? And so the microbe has to use up some ATP, prime the pump, so to speak. Now, I'm not going to say what you have at the end of stage 1. So you don't have to memorize this term. It's okay. Just what is going on in stage 1. You're using ATP to phosphorylate those molecules. Okay. Stage 2. In pink. So there's a couple of things here to think about. So what's happening of consequence during stage 2 for the microbe?
Generating ATP and NADH.
Yes, on both. So generating ATP, if you're a microbe, you care about that for sure. And then NADH is also very useful because it can be used, if necessary, for stage 3. You can see down here, the brown box is NADH. So this NADH that you see down here is actually coming from stage 2. Okay, so NADH is getting generated. ATP is getting made. How is ATP getting made? What's the process here in general? There's a term for this. Awesome. Substrate level phosphorylation. Just means that you have a phosphate attached to a substrate. And that substrate will say, here you go, ADP, I'll give you a phosphate. And so substrate level phosphorylation, if you hear the term phosphorylation, think about ADP. ADP is trying to get phosphorylated, become ATP. Okay. Stage 2, I would like you to know what the final product is of stage 2, which is what? pyruvate. That one I want you to know. Because that's what I call the decision point for the microbe. So once the microbe takes that glucose, runs stage 1, stage 2, and it gets pyruvate. Okay, so that's important. Let me go back. Whoops. Okay, whoops. So, all right, so stage 2, we have ATP being made, NADH being made, and we end up with pyruvate. Okay, what was the other question I had for stage 2? Stage 2. There's substrate, oh yeah, substrate level phosphorylation. Oh, what's your net ATP by the time stage 2 is done? The net, not the total gross, but the net. Or did I say that the right way? You net me, yeah, you net 2. It's Monday, sorry. So you use up 2, you make 4, so you net 2. All right, let's think about stage 3. So let's say because of the habitat the microbe is currently in, its decision is, yep, I got to continue on with stage 3. That's what I'm going to do. So that's in the green area. Couple of things to take note of here that are of importance. Can you think of one?
NAD plus is generated.
NAD plus is generated. That's a big deal because the microbe can then use that back in stage 2. So that's just to keep this going, like, because NAD plus, NADH, those aren't in abundance for the microbe. Okay, the microbe has very limited supply of that. So it's got to constantly make and use. And if you generate the NADC plus at stage 3, that can make sure that stage 2 keeps going. And so if you're a microbe and you're forced to do stage 3, you definitely want to do a lot of glycolysis, because remember, with fermentation, they don't get a lot of bang for their buck. So they really have to eat a lot in order to stay alive. Okay, so that's one good thing. Another thing to note here is, let's look at the actual end products of what they're showing here anyways. You got ethanol. I think ethanol is a good example because a lot of us are aware of the brewing industry and production of ethanol. What's the chemical makeup of ethanol, chemistry people? CH2, ethanol? CH2OH, right? Isn't that it? Is that CO2? Is carbon dioxide the same thing as ethanol? So take note that when they get the final products, it's not all carbon dioxide. So why is that important? Well, we say that if you can break something down, if you can start with an organic molecule of glucose and break it all the way down to CO2, that's your best situation. You get more bang for your buck that way than if you're left with a partially broken down product. So ethanol is a partially broken down product. That's not as good. You're not going to get as much ATP leveraged out of that. So it's not directly saying that here, but in some of the other slides in this slide set, or one of the slide sets, we talk about that idea that it's not a complete breakdown like what we see with the citric acid cycle and all of that. Okay. So let's go back to stage 2. If your E. coli, remember E. coli is a facultative anaerobe, so they're very flexible. But if you're a smart E. coli, you're going to get down to pyruvate and then you're going to pause and search. What are you searching for in your habitat? Oxygen, okay? Oxygen is the best electron acceptor. That means if you can employ oxygen in your physiology, you will get more ATP than any other method. So pyruvate, it would make much more sense for E. coli to get to pyruvate, say, do I have oxygen? Throw open that pantry and say, is there oxygen? And if there is, don't do stage 3. That's not very efficient. Instead, send pyruvate into what next? The citric acid cycle. That's the next step. Okay. Aye. Okay, so citric acid cycle. So thinking about, we started with glucose, made it all the way down to pyruvate, and now you can see pyruvate getting shunted over to the citric acid cycle because E. coli is like, I know I got oxygen, so this is my next step to be efficient. And now you see that the carbon dioxide is coming off, you're breaking down pyruvate all the way now to CO2. So that is, chemically speaking, that would allow for the most energy capture if you can do that, have a complete breakdown. I would like you to know the very first step of the citric acid cycle in the sense that we're going to say that we're starting with pyruvate. Let's keep it simple. We're going to start with pyruvate. And then you have NADH being made as you come into it. And then know that you're going to be reacting with oxaloacetate to get you citrate. That's why they name it the citric acid cycle. That's the first stable molecule in the cycle. So this first portion here, I would like you to be able to at least recognize it. Okay. But then after that, no, you don't need to know the details, but you need to know how the microbe benefits from doing the citric acid cycle. So we already talked about the complete breakdown of pyruvate to CO2. What else is going on here? GTP and NADH. What? There's another one. Yep, FADH2. What is GTP just in general? What is that? Yeah, it's an ATP equivalent. Essentially, it's an energy molecule. And very often a microbe will make GTP and then convert it to ATP. Not always, but anyways, so that's good. That's why it's in red. It's like, ooh, that's similar to ATP. And then you have the NADPH, NADH, FADH2. Depends on the microbe if they're going to do NADPH or NADH. That's no big deal. You don't need to know that. But certainly that you have these. What are NADH and FADH2 called again? What's Tinkerbell? Electron carriers, reducing molecules, energy carriers, electron carriers, all of those terms apply. Okay, so, well, that's all good. I think that's pretty good of what we covered there. So no, you don't have to know every single step. You just have to think about from the micro's perspective, what's the payoff here? What is the goal? What is the microbe getting out of this? Okay, so now, remember now, this E. coli didn't know that there's oxygen in the habitat. So this isn't dealing with oxygen yet. We need to think about the next stage now. So now that it's made the NADH and the FADH2, it's done its job. The citric acid cycle is good. Now what has to happen? Where do we go next? Electron transport chain. Where physically is that for the microbe? Membrane. Remember, they don't have mitochondria. Okay. Now, mitochondria were once free-living ancient microbes. Sure. But current existing microbes don't have mitochondria inside them. So now we zoom to the cell membrane. So now we have to imagine the Tinkerbell NADH and FADH2 are flying over to the cell membrane. So that the electron transport chain process can happen. So E. coli knows there's oxygen. So this is where oxygen is coming into play. So this is happening in the cell membrane. And again, you don't have to know the agonizing details. However, knowing how the citric acid cycle links into the electron transport chain. So how does it link into the electron transport chain? The electron carriers. Where are they showing up here? Which complexes? You read from where you're sitting? 1 and 2. Okay, complex 1 and 2. So that's, at the kickoff of the electron transport chain. You have the NADH comes in on complex 1, FADH 2, it's complex 2. And what you see happening is they're electron carriers. So they're donating off electrons. And there's pumping of protons going on. So how would you describe what's happening in the big picture here? What's going on with those electrons? Yeah, shuttle from complex to complex, donor to acceptor, on down the line. Hot potato. Okay, you got these electrons flowing from donor to acceptor. And it provides a mechanism. That whole process provides a mechanism for the microbe to do one other hugely important thing. What is it? Proton gradient. Why do we care about a proton gradient? Why does E. coli care about a proton gradient? Yes. So once you get a proton gradient, that's like potential energy that can be used to do something. Most of the time, E. coli is going to choose to make ATP. But proton gradients can do different things for the microbe. It's not always ATP, but in this case, and again, the artist should have put the ATP synthase here because that's a huge goal of the electron transport chain is to get the protons diffusing through, whoops, where'd it go? Diffusing through the ATP synthase. As they go through that complex, it's going to provide the mechanism, the torque force actually, to combine a phosphate onto ADP. So this is not substrate level phosphorylation because you're dealing with a proton gradient linked to an electron transport chain. So if it's not substrate level, what's the other method we've been learning about?
Electron transport linked phosphorylation.
Very good. Electron transport linked phosphorylation. Oxidative phosphorylation is how people outside of microbiology talk about it because they're so focused in on oxygen because we're very human centric and that's what we do. We use oxygen. Okay, so please remember you're in a microbiology class. There are no mitochondria in microbes. And it's electron transport linked phosphorylation because you do not always have to have oxygen at the end as the terminal electron acceptor. And actually the term oxidative really isn't referring to oxygen anyways. It's referring to oxidation, the stripping of electrons off of a molecule and then given off to a donor.
So would oxidative be incorrect on the exam?
No. But I will be asking questions to get at the idea that microbes don't always have oxygen at the end. And that you can demonstrate, that you understand that. It can be something else besides oxygen. So in a microbe world, oxidative phosphorylation has to be defined more loosely. It's an electron transport linked phosphorylation event. So E. coli started with glucose, went through glycolysis to pyruvate, said, oh, I have oxygen in my habitat. I'm gonna shift over to the citric acid cycle so I can generate some FADH2 and NADH, break down my pyruvate all the way to CO2, get a little bit of energy, DTP, and then I can link that into the electron transport chain, get my electron carriers, my Tinkerbells over there, donate electrons, pump some protons, get my proton gradient, which then yields a lot of ATP if oxygen is the terminal electron acceptor. So I really like this picture because it puts it all together rather than when I learned biochem, I had to learn everything discretely and never really saw how it all fit together, at least when I was being taught. So I like how this image is really linking what's going on, that it makes sense when you start to kind of pull back from it and look at the big picture here. How does the microbe gain from this? And so in this case, they are saying, yes, oxygen is the terminal electron acceptor. Here it is happening in the electron transfer chains happening in the cell membrane, and they're trying to show that you get a lot of ATP from that process. Okay, so glycolysis, citric acid cycle, or the TCA, or the Krebs cycle, electron transport chain. Questions on any of those? Yes.
In the textbook for the citric acid cycle, it says it produces 3 NADH, but all the slides say it produces 4.
You won't have to know numbers. Don't memorize numbers. I don't, again, zoom out, like just in general, it makes NADH and FADH2. No. But let me just look. Yeah, I have 4. They're probably not counting the very first one, is my guess. They're just looking at the actual cycle. And then that's 3 if you just look at the cycle. But if you look at how pyruvate comes in and links into it, there's another one. Other questions on glycolysis, citric acid cycle, electron transport chain?
Oh, and then the only like number that we have on is for step 2 of glycolysis, which is 2 ATP.
Yes.
Okay.
And even like that last slide where we were looking at 34 ATP being made, you don't even have to memorize that. But if you can express that using oxygen as the terminal, you get the most ATP. That's really all I'm going for. Other questions on these processes? I know a couple of you did mention you were a little shaky on how in-depth you have to go. And I'm hoping this is helping you figure out that much more interested that you are able to link these, what we just talked about, how they link together, what are the payoffs for the microbe? And then really, when we looked at it, a huge payoff is how much ATP they are getting. So, and they can get it a couple different ways, because glycolysis is substrate level phosphorylation to create ATP. Then the electron transport chain, it's oxidative phosphorylation or electron transport chain linked phosphorylation. So think of it that way. So I will post these, but we've been working through this. But, okay, so let's say you're E. coli. Why might a microbe decide to undergo stage 3 of glycolysis? So E. coli pauses at pyruvate, looks around. Why will it say, oh, okay, I'll do stage 3?
There's no oxygen.
There's no oxygen. So now let's kind of tease that apart a little bit. So we have learned that when there's no oxygen in the environment, yes, you can do fermentation, but there's actually a slightly, well, actually quite a bit better option. There is another option we've talked about where the microbe will forego stage 3 and do another process. What do you think that is? So we said oxygen is the best electron acceptor, the best terminal electron acceptor. So if E. coli is looking around and says, darn it, no oxygen, what might they do instead besides stage 3? If it's a smart E. coli, it's going to choose a different option. So what other metabolisms have we learned about?
Other, like, instead of oxygen, there's like other chemicals they can use.
So what's that called? If they're not using oxygen,
Anaerobic.
they're anaerobic, yeah, anaerobic metabolism, anaerobic respiration. So if you're E. coli and you're like, okay, I made pyruvate, where's my oxygen? Ah, darn, I don't have oxygen. If you're smart, you're gonna say, well, could I still do an electron transport linked phosphorylation and just not use oxygen, put something else there instead? That would be the second best option for E. coli, because running an electron transport chain process will get you more ATP for sure than stage 3 of glycolysis. Stage 3 of glycolysis might get you a little bit of ATP, but anytime you can run an electron transport chain and generate a proton gradient, that's better. Okay, so anaerobic respiration. So we just kind of answered some of this. What's the major difference between aerobic and anaerobic respiration or anaerobic metabolism? We just said it's something, anaerobic means there's something other than oxygen as the terminal electron acceptor. But there's another thing to think about here from the microbe's perspective. When it runs anaerobic respiration, what does it have to worry about in terms of ATP production? That's phrased the right way, but think about how much ATP it produces in these two. Which one's better?
Aerobic is better.
Right, because oxygen is the best electron acceptor, which means you're gonna get more ATP using oxygen as the terminal electron acceptor than any other molecule that we know about on Earth, okay? So anaerobic respiration is similar to using oxygen, it's an electron transport chain process. It's proton pumping, getting proton gradient. It's just that they use something else besides oxygen. And they're going to try to find something that's close to oxygen on the electron tower. So we said oxygen is the best, that's why it's always at the bottom here of the electron tower. But if I'm E. coli, I'm gonna be looking for some Fe3+, the ferric form of iron, or I'm gonna be looking for nitrate. And stuffing that on the end of my electron transport chain if I don't have oxygen. Because that will still get you a pretty decent amount of ATP. So the farther the electron falls on this tower, the more energy you get, the more ATP you get. That's the rule of how they set this up. The farther the electron falls, the more you get in terms of ATP. I'll come back to that slide. So that is kind of getting at the comparison here. Still have an electron transport chain process, still have proton pumping, slightly different flares. You don't have oxygen. And they're trying to show there's less proton gradient per run, which just means that it's not as good as having oxygen in terms of how much ATP you can make. You don't have to memorize numbers, just general, like it's not as good. You don't get as much ATP, that's fine. Questions on anaerobic versus aerobic? Okay, I think we've answered all of those. Answered that. Okay, what about this one? This is another concept that we covered that we can't do. But a lot of the microbes that are responsible for recycling elements on Earth, the chemolithotrophs, are very, very fundamentally important for that. So chemolithotrophy. So troph means to use or to eat. Litho is referring to what in general? Rocks, which are inorganic. So if you can link that a rock is inorganic. So they're eating rocks. They're stripping electrons off of inorganics. So we can't do that. We have to eat something that was organic in order to do that. So this is actually an example of chemolithotrophy, okay? In this case, they're showing hydrogenotrophy. So hydrogen is inorganic. So you're stripping electrons off of an inorganic into an electron transport chain. So they're showing the electron transport chain. And you have a terminal electron acceptor. In this case, it's oxygen, which is the best choice, but it's not always oxygen. So when we talk about chemolithotrophy, we're kind of looking to the start of the electron transport chain. What is getting stripped of electrons? And in this case, it's hydrogen. H2 gas is, microbes are really good at producing H2 gas. Can you think of what other microbes might be hanging out next to a chemolithotroph? How would they be producing hydrogen gas? What kind of pathway might generate hydrogen gas? Can you guess? Yeah, fermentation. So remember the phenol red lactose glucose sucrose tubes you did in lab with those little tiny Durham tubes in there that would capture gas. So some of that gas could have been CO2, could have been H2, depends on which pathways they were running. And so hydrogen gas is made by a lot of microbes who are forced into fermentation. So fermentation would be, like if I was E. coli, that would be my last choice. I'd be looking for oxygen because I'd want to do aerobic respiration. Then if that wasn't possible, I'd do anaerobic. If that wasn't possible, then I'd sigh and say, all right, I guess I'll do stage 3 of fermentation. Get a little bit of ATP, but it's not the greatest. But at least it's better than nothing. Okay, so an electron, a chemolithotroph is using inorganics as the electron and energy source. So let's see, do I have that in here? Where did it go? Let me go back to this slide. Remember, photosynthesis will not be on this. So hydrogenotrophy, these are different examples. So in all of these cases, in these big picture equations that are being shown here, hydrogen is the electron donor. Okay, so hydrogen is getting stripped of electrons in this process. And you can see sometimes oxygen's there as the terminal electron acceptor, but not always. So hydrogen, if chemolithotrophs are hanging out near microbes that do stage 3 fermentation and produce a lot of hydrogen gas, that's awesome because then they can grab hydrogen and strip electrons off of it. So very often you will see those types of microbes hanging out with each other. Questions on chemolithotrophy? Okay, let's think about this for a little bit. The electron tower, a couple of you mentioned that you were still unsure about this. You filled out the form on Friday. So here we're looking at, you have to know some rules. First of all, when they have them set up in pairs like this, divided by that slash, you have to know that the pair that's lost electrons is oxidized is always on the left of the slash. And the partner in the pair that's got all of its electrons, it's fully reduced, is to the right of the slash. Okay. So that means, and then we have the reduction potential scale here from starting at nice negative numbers up top to 0, and then nice positive numbers toward the bottom. And you have to understand that that means that if it has a negative reduction potential, that means that the reduced partner is very happy to donate off electrons, very good at it. The more negative the number, the more willing they are to do this. Very happy, a happy Tinkerbell, I'm gonna donate off my electrons, okay? And then as you get into the positive scale, it's the partner to the left of the slash that's like, yeah, give me an electron. I'm really happy to take that electron. The more positive the number, that's why oxygen is the best electron acceptor. It is at the bottom with the most positive number. That means oxygen is so hungry and so good at taking electrons and accepting electrons. So what's going on here? We have carbon dioxide acetate pair that is at a negative 0.3 reduction potential. The ferric and ferrous pair is at a positive 0.2. So which pair would be the one that has to be donating electrons? Someone in that pair donates. Which one or two? One. Why?
Because it's negative.
Because it's negative. Awesome. A negative reduction potential means one of these has to donate. It's gonna be which one? By convention, the reduced partners to the right of the slash. Okay? So that means it would be carbon dioxide or acetate. What you think?
Acetate.
Acetate is the happy partner there, like Tinkerbell. I'm fully reduced. I have the ability to donate off electrons. So acetate would be the one. And then who in this pair would actually receive or accept the electrons? Think about the rules of who's on the left versus the right of the slash. So acetate donates, who's gonna be there to accept?
Plus.
The 3+. So the one to the left is the oxidized version, and that means they're ready and capable of accepting electrons. So if you were to write this out in a reaction, you would say acetate plus Fe3 plus, Aero, CO2, and Fe2 plus. So in order to put that all together, you do have to know the rules of the electron tower. Okay? And what the reduction potential numbers mean. Well, once you know that, then you can put all of these into combination, you can write equations, figure it out. Questions on this? Please play around with this a little bit as you're studying. Do I have? Okay. Can I please get your feedback? All right, so can you get into Educat? And I have an in-class. Okay, so in the in-class activities section, I should have today's date, 2/16/26. What is still an issue? Could you please give me some feedback on that based on what we just covered together? I'll look that over before Wednesday. And then once you're done answering that, you're free to go. We're not going to do any more. Yes.
Like the person who reads sulfur bacteria gonna be on the test or not?
Nope, no photosynthesis. It'll go up to the slide on halobacterium where it says not quite photosynthesis. That's the stopping point. Oh, one other thing before I forget. There's more essay questions on this exam. Okay, it's going to be. I don't have it all figured out, but there's going to be a couple short answer and then several essay. Mhm. Yeah.
I look over now. Yeah.